Okay, periodic trends. This tends to be the bane of some students' existence, which I don't understand, but because I know how much y'all struggle, I don't want to teach this. I hate this because of that. But I'm here to tell you it's not hard. You can use the same two explanations, shielding and effective nuclear charge, to explain all of these trends. So we're going to go through each one of them, talk about any exceptions, and talk about how I want you to actually format your answers. Okay? As an AP grader, I have my ideal, like what I would like to see, and what I'm going to tell you is what kind of we're looking for. So really quick, let's just go ahead and make sure we know the definitions of the trends we're talking about. Atomic radius, kind of duh, is the radius of what? Radius of atoms. So we can compare atoms' radius or radii by looking at the trend on the periodic table. In AP, they're going to tell you what's bigger and smaller. You don't have to do that, but your job will be to explain, and that's the difference between Chem 1 and Chem 2. The ionic radius would be the radius of ions, and we're going to do lots of examples of those. Electronegativity. Electronegativity, who remembers that? How much close? It's the attraction of electrons to an atom, but it's specifically in a bond. So only things that bond can be categorized with an electronegativity value. So if you look at an electronegativity table, they won't have any values for the noble gases because those typically, not always, they typically don't react. Our larger ones do, but they don't have those electronegativity values. Ionization energy, who remembers that? Energy required to do what? Naira? But what is the energy to become an ion? What's happening? What are we removing? An electron. It's the energy required to remove an electron. Now, on occasion, they'll ask you to write an ionization energy equation describing something. Students freak out. I don't know how to write an ionization energy equation. Yeah, you do. If I have element X and I remove an electron, what do I have left? X plus. That's an ionization energy equation. Not a big deal, okay? All right. Next up, we really do need to add, there's one more here that's not written down. It's electron affinity. Electron affinity is the energy required or energy acquired when an atom, this is a horrible definition. I'm going to take off energy required. Even though it's an energy value, it's just basically the attraction of an electron to an atom in a gaseous state. In other words, you have an atom hanging out, and it's either going to attract an electron or not attract an electron, right? And that is an energy. If you want to make that attraction happen, you'd have to force it and put in energy. If the atom is really excited to get an electron, it's just going to grab one and energy is going to be released. Okay? So in general, it's an attraction. I don't know. Well, it's up to you. I don't know. I mean, I just deliver the message. Okay. Atomic radius. Let's start with our first one. The general trend, let's talk about the general trend. Put the phone away. The general trend is as you go across the table, what happens? Size decreases. As you go down the table, size increases. That's easy. That's not going to be enough for this class. You're going to have to do some explaining. You got some explaining to do. So as you go down the table, we know it gets bigger and bigger and bigger. Can anyone tell me why? Noah? Correct. The number of energy levels increases. You can say that. Francium has more energy levels of electrons than sodium does, therefore it's smaller. Or you can use the fancy word shielding. Shielding increases as you go down the table. So you can say francium is more shielded or has more shielding than sodium. What does shielding mean? It just means the valence electrons are shielded from the nucleus, so the nucleus doesn't have quite that pull. So if I look at lithium's valence electrons, they're really close to the nucleus, right? Francium's valence electrons are shielded by all of these energy levels. So there's not a lot of pull on this guy. So it's going to be a bigger atom. Okay? Shielding is acceptable. You cannot use shielding when you talk about going left and right. Is shielding changing when you're going left and right? No, we're not adding energy levels. We're adding electrons and protons to the same energy level. All right. Going across. We said it as we go across. Is this going down? Oh. This is our across thing here. In general, as we go across from left to right, we get smaller. What does that have to do with? Why? Yes? Correct. We are adding, as we go across, we're adding protons to the same, if you feel, go ahead, you can always watch the video, same energy level. We're adding protons to the same energy level. Since we're adding more protons, we're adding electrons too, but those are the same level, right? Since the protons are being, God, I'm having a bad day today. We're adding electrons, my B, to the same energy level. Protons are increasing both as we go across and as we go down, right? So it's the addition of electrons to the same energy level that is making the extra protons that are being added stronger and stronger and stronger in comparison and pulling in those radii, pulling in the extra electrons, okay? What we call that in fancy terms is our effective nuclear charge. That's the terminology I want you to use. So why is fluorine smaller than carbon? Because fluorine has a higher effective nuclear charge, and that's all you have to say. And you can use effective nuclear charge and shielding to describe everything. So is everyone good with understanding that? If you get a little deeper into the whole effective nuclear charge thing, that is proven with a calculation called Z-effective. You don't have to do the calculation, but it's interesting. To calculate Z-effective, you just take your number of protons, your atomic number, minus the core electron, number of core electrons, and you get a value. The value standing alone doesn't mean anything. You have to compare the two values. But what's really interesting about this is there's actually a faster way to calculate it. If I have a neutral atom and I have a certain number of protons, how many electrons do I have? Neutral atom. Huh? The same. So this is actually your number of total electrons. What is my number of total electrons minus my number of core electrons? Valence electrons. So really, Z-effective, its calculation, is equal to the valence electrons. So we can compare by looking at, let's take a look at, again, that carbon and fluorine example. What's carbon's Z-effective number? Valence electrons is 2, really? 4. And what's fluorine's valence electrons, or Z-effective? That's what we're talking about. 7. The bigger the Z-effective value, that means it's got a stronger nuclear pull. Effective nuclear charge is kind of the same as nuclear pull. So this is a comparative number. Fluorine has a higher Z-effective, so it's smaller. Okay? You cannot use Z-effective or effective nuclear charge when you go up and down a column. Why? If we're comparing sodium and francium, what are their z-effectives? The same, okay? They're both a z-effective of 1. So you can't use z-effective as an argument unless you're going across, just as you can't use shielding unless you're going up and down. So let's answer these. Sodium, which should be larger? Why? Sodium versus chlorine. Sodium is larger. Why? Has a lower effective nuclear charge. I'm a fan of the effective nuclear charge over the Zeph. When you say Zeph, it kind of leads to needing a number, and I feel more confident in what you're saying when you say effective nuclear charge. Which should be larger, lithium or cesium? Cesium, why? Okay, don't say shielding. That would not be enough. You have to say, does it have more or less? Just saying shielding, and I'm glad you said it because it brings up a point. If a student writes shielding, that's not enough because you're not telling me if it has more or less shielding, okay? So cesium has more shielding. So we're not asking you to write a ton, but we're not asking you, you can't just write one word either. Yeah. Okay, if we did lithium or magnesium, level takes precedence. Yes. Lithium versus magnesium, we're going to say magnesium because shielding, I before E except after C, shielding, because level takes precedence. That was a good question. I can tell you, though, on the AP, they're not going to do something like that to you. But we're just, level is going to have more of an effect, change in level. Okay. Y'all ready for ions? All right. Here's the thing about ions, and I'm going to talk to Ms. Rozier, and we're going to get on the same page here, that in order to get any credit for any comparison of things with comparing different ions, you have got to talk about the proton to electron ratio. There are too many students that miss this. When I grade the AP, and I'll give an example of what students do that's just really wrong, and it's just not enough information, and I can't give them full credit. I have to know, tell me about the protons and tell me about the electrons. Both of those have to be addressed. If you don't want to separately address those two values, go ahead and talk about a ratio instead, okay? But we got to hear something about both of those things. So ions compared to their own neutral element. So say we have silver plus versus silver. I want to hear about both of these things. Tell me about silver and silver plus. What do they have the same? Yep, they have the same number of protons. Say it. Same number of protons. But then, what else do we know? Ag plus has one less electron. So what happens? So what does that do for Ag plus's proton to electron ratio? Ag plus has a higher proton to electron ratio. And what does that do? Doesn't that pull on the atom? So that makes the atom smaller. Making the ion, making Ag plus smaller. You've got to address both things. What's the same or what's different? You've got to say they have the same number of protons because not all positive things are smaller than neutral atoms. Cesium plus 1 is not smaller than fluorine, okay, just because it's a positive. What makes this positive smaller is we're comparing something with the same number of protons, okay? So we can say, a general rule we can say is that positive ions are smaller than their own neutral atom. Okay, I've run out of space, so I'm going to extend the heck out of this page and talk about S and S minus 2. What do they have the same? Hello? Same number of protons. But what can you tell me about S minus 2? Has 2 more electrons. Doing what to the nuclear pull? Or that proton to electron ratio? Decreasing the proton to electron ratio, making S minus 2 bigger. Now, there are some explanations out there, and I just don't think it's as good of an explanation. But some people say because there's more electrons with the same number of protons, those electrons have repelling forces which expand the cloud. Not that much. Not as much as the effect of that change in proton to electron ratio. That's a bigger impact. That I would prefer if you didn't use the electron repelling as an explanation. However, if you see it in a multiple choice or something, you can go ahead and pick it because it is slightly changing that cloud, but not as much as that nuclear pull. Okay? So are we good with ions of their own neutral element? So what's our general statement? Negative ions of an element are bigger than their neutral ions. And that's true. Neutral atoms. Okay, now let's talk about ions in the same family. This is super easy. If we have F minus and Cl minus and Br minus, how do we rank them in size? Yeah, by level. Because they're in the same group, we can just follow the normal trend. That bromine has more shielding than fluorine, right? What we're really doing, though, is looking at the noble gases. This is really isoelectronic to Cl. This is isoelectronic to Ar. And this is isoelectronic to Kr. So when in doubt, find out what noble gas these things are isoelectronic to. This is the biggest because it's most shielded. And this is the smallest. So Br minus, in turn, is the biggest. Okay? So that one's easy. Same thing, group ones. So in the same family, we're talking about up and down. You can just use the trend. Now, this one is the big one right here. Hugely important. Ions that are isoelectronic to each other. All right, so we're going to want to compare S minus 2 to Ca plus 2 to argon. I don't want you to freak out and there is no way you can use the periodic table and just point to where the ions are. That doesn't work, okay? What I want you to do is stop and find out, are these isoelectronic to the same thing? If not, I can kind of rank them. We'll do 2 examples. I'll set up another example in a minute. But what noble gas is S minus 2 isoelectronic to? Argon. What noble gas is Ca plus 2 isoelectronic to? Argon, and argon is argon. So we're basically comparing things that all have the same what? And that's what I need you to state. You have to say they have the same number of electrons in your answer. Because nothing you say about the protons will have any meaning if you don't state that, oh, but they have the same electrons. So if they have the same number of electrons, which ones are going to be small? The ones with more or less protons? More protons. So the ones with the most protons are going to be smaller. You could go to the periodic table, sure, and look at S and look at Ca, but there's another way to tell. You see the charges? Doesn't that plus 2 mean there's more protons than electrons? So wouldn't that be the smallest one? So you can say Ca plus 2 has the least number of protons, or proton to electron ratio, whatever, we know we're comparing the same number of electrons. Has the least number of protons, therefore it's the largest. I mean, smallest, shoot, sorry. Way to confuse people. Therefore, it's the smallest. Oh my God, y'all. I'm sorry at home. Ca plus 2 has the most number of protons. All the electrons are the same. Most number of protons because it's got a plus 2. There's 2 more protons than electrons. Most number of protons means it's the smallest because it's got a stronger nuclear pull on said electrons. What is the middle one? Which one's in the middle? Argon's in the middle, okay, because it's got an equal proton to electron ratio. And then S minus 2 is your largest because it has the least number of protons pulling on the same electrons. So as a reader, I've seen answers that students have given that say things like, oh, calcium has the most protons, so it's the smallest. That's not enough. Why is that not? Because I could compare it to bromine. Bromine has more electrons than calcium, right? So you've got to mention the electrons. The reason it's the smallest, it's got the most number of protons pulling on the same number of electrons. Do y'all get that? So I want you to always talk about protons and electrons when you're doing these answers. So what about a question, I wrote these down, P minus 3, CS plus 1, and Cl minus. I want to rank those from small to big. What's your first thing you're going to do? Exactly, find out what they're isoelectronic to. P minus 3 is isoelectronic to argon. What's CS plus 1 isoelectronic to? Xenon. And what's Cl minus isoelectronic to? Argon. So you have to rank these gases, right, based on their size. So which is the largest? CS plus 1 because it's xenon, so due to shielding, this is going to be the largest. Do you see how it's a positive, but it's the largest, as opposed to a positive being the smallest? Okay, that's because they're not isoelectronic to each other. But these two are. So we're going to have to compare them. Which one is going to be the next largest? Next largest. P minus 3, because this guy has a smaller proton to electron ratio. These are isoelectronic. They have the same number of electrons, but argon has less protons than, no it doesn't. We're doing phosphorus, it's not argon. Phosphorus has less protons than chlorine does, right? So it's going to have a smaller nuclear pull. So the bigger the negative charge, if you're comparing things that are isoelectronic, the bigger it's going to be because there's less pull. And then the smallest one would be Cl minus. Okay? So again, students miss points when they don't identify the fact that, oh, these have the same protons, or oh, these have the same electrons. Talk about both items. I can't stress that enough. So you will not get credit if you don't talk about both. All right. Any questions on that before I move on? Examples that might throw you? Nope. Okay. Electronegativity. Electronegativity we know is, in general, the attraction of an electron to something when it's in a bond. So I like to use road maps. I like to know that what's my most electronegative element? Fluorine, and the least? Francium. So fluorine is the most, francium is the least. If you know that, you know at least the direction of the trend. Now, you can't say, oh, this is more electronegative because it's closer to fluorine. You can't. That's an observation, not an explanation. So you can't use the trend in the explanation. So what we're going to do is look at the trend and talk about why. So as you go across the chart from left to right, what happens to electronegativity? We're getting closer to fluorine, right? So electronegativity does what? Why? Why does electronegativity increase? What? Louder, guys. Right. Not shielding's the same. We can't use shielding. There's higher what? Effective nuclear charge. Bring it all back down to those two descriptions, because that's the reason. Because the pull is greater, it's going to be more attractive, more attracting to electrons and bonds. With fluorine, remember, being the highest. Right down there we have fluorine, the floozy. Here she is. She looks like a little hoe. There's fluorine taking away electrons, wanting electrons wherever she can get them. And this is francium the freak. Francium the freak will pretty much donate electrons at any time. So you can imagine those two getting together, francium and fluorine. And that is super reactive. That's probably our most reactive reaction, which we don't do because francium is, hence the one eye, he's a little radioactive. So we don't tend to practice that. So as we go down the table towards francium, what happens? Electronegativity does what? Decreases. Why? Because as you move down the table, what happens? More shielding. Those valence electrons are more shielded, so they're easy. They're not as attractive. The nucleus itself is not trying to pull in a bunch more electrons. Francium's like, I don't want any more. Okay. Most often your metals are, not most often, metals always give away electrons. Metals are always positive. They're never negative. So because of that, they're going to be, that side of the table in general is just going to have a lower electronegativity. Okay? All right, moving on to the tough one now. Ionization energy. Ionization energy is the amount of energy required to remove the most loosely held electron. And it says in a gaseous atom or ion. So we talked about how to write this. Very important. Now, you can have multiple ionization energies. You can take off one electron, you can take off two electrons, you can take off as many as you want. And it's going to get progressively harder, right? If you take off one electron, what happens? You become what kind of ion? Positive. So taking off a second electron is going to be even harder. Using these trends, you can answer questions about a series of ionization energies. Magnesium, when you take off its first electron, it takes about 735 kilojoules. When you take off the second electron, all right, that's cool. It takes more joules. We knew we expected that. But look at from here to here what happened. See that huge jump in energy? Why is it so much harder to remove magnesium's third electron? Look at the periodic table. It's a core electron. Removing core electrons is really, really hard. Removing core electrons, you see a jump in energy. So they can ask you questions like these to ask you to identify an element. You know, if you see a big jump between the first ionization and the second ionization, it's probably a group 1 metal, right? If you see a big jump between the second and third, it's a group 2. So you can utilize this information to figure stuff out. And this is why magnesium is +2. It's not going to, we can't readily get that much energy to make a +3 happen, all right? So you need to be able to use ionization energies in this matter. But as far as the trend goes, in general, as you go across the table, does it get easier or harder to remove an electron? Harder. Why? Yeah, we have a stronger nuclear pull. Our effective nuclear charge is increased. As we go down the table, what happens? It gets easier because shielding makes the nuclear pull less, so it's easier to remove an electron. All right? So those are our general rules. But like everything else in chemistry, we've got exceptions. And you always get asked about the silly exceptions to ionization energy in this unit. So this picture I showed you, I just wanted you to see is graphing ionization energies from atomic number 1 all the way through the periodic table. So as you go from hydrogen to helium, it increases, right? And then as you go to this from row 1 to row 2, that's going down the column, it decreases. So notice there's a decrease as you go down the columns, right? But what we're interested in, look as you go across level 2. It's generally a trend upward, right? But notice there's 2 dips between B and E and between N and O. And this dip happens on every single level. So there is an exception. I'm going to set up kind of a format that is a useful way to answer these questions. If you draw the electron spin diagram, it's going to save you a ton of words when you're describing. So let's talk about nitrogen and oxygen. Really quick, let's go ahead and draw out the spin diagram for the orbitals. We've got 1s, 2s, and 2p. So nitrogen has 1s2, 2s2, and how many in 2p? Not rhetorical. 3. All right. Oxygen, however, is 1s2, 2s2, what? 2p, 4. All right. When you're answering this, I really want you to indicate which electron we're talking about. We're talking about the last electron in these things. So we're talking about that electron and that electron. Please indicate that so the reader knows you know what you're talking about. Okay? So the last electron in oxygen is supposed to be harder to remove. As you go across the table, that's what the trend says. But in actuality, the last electron in oxygen is easier to remove. Why? Look at those 2. Look at them in the picture. Why would that second electron in that orbital be easier to remove than the last electron in nitrogen? Amelia? No. Naira? Repelling forces. Remember, this is a negative electron now sharing its space. There's a statement in a lot of textbooks that say half-filled orbitals are more stable. That is true, but it's not something that on the AP they take, and a lot of students just learn that. Half-filled are more stable. That's true, but it's not a reason. Why are half-filled orbitals more stable? Because filled orbitals have repelling forces. So, last electron in oxygen is easier to remove due to the repelling forces with its other p electron. I'll put other p electron in that orbital. It's in the same orbital. Okay? So by drawing that, it gives me comfort that you know what you're saying. If you don't draw it, you're going to need to say the last electron in nitrogen is in a p that is unpaired or something. So I know. And then the last electron in oxygen is a paired electron sharing a p orbital. You need to say this in words if you don't draw it. That's why it's easier to draw it, because we can see what you're comparing. Okay? So this is true down the whole column, P and S, between P and S, AS, and SE, and they won't ask you about lead and tellurium and bismuth and polonium. They won't. So those first 3 are where you're going to get the questions. So are we good with that one? All right, now let's do the boron to beryllium exception. And again, I want you to draw out your spin diagrams, because here's the thing. If you draw your spin diagram out, you don't have to memorize it, because you'll remember it when you see it. You'll remember, oh, that one has repelling forces. This one, oh, this one has to do with the S and the P thing. So this is just 2S and 2P. So boron has 2sp1, and this has 2s. Wait, did I do it backwards? Oh, that's fine. All right. So as you go across the table, this electron in boron is supposed to be harder. But it's not. It's supposed to be harder because it's to the right. So why is this one easier to remove? This is a weird one. I don't expect you to know this without, and pre-AP we did cover this. Yep. It has to do with the shape and proximity of the p orbital. So I'm going to write down shape and proximity. Those are the words I want you to use. So p orbital, if you look, is slightly further out than the s orbital. So at times, on average, it's going to be easier to remove that p than the s because the s penetrates the area around the nucleus more often. Okay? So, supposed to be harder, but it's easier to remove due to the shape and proximity of a p orbital to the nucleus compared to an s orbital. If you need to go back and watch the video to get all the words again, you can. That's what the videos are for. So boron, beryllium to boron, magnesium to aluminum, those are the only two I've ever seen on the AP. I wouldn't expect to see anything different than that. So let's do these real quick, and then we got to move on to electron affinity. Which atom would require more energy to remove the most loosely held electron, and why? Sodium or chlorine? Chlorine, why? Higher effective nuclear charge. Which atom would require more energy to remove an electron? Lithium or cesium? Lithium. Why? Less shielding. And in this case, we're talking about removing that electron, right? So there's more nuclear pull. So it's harder. It's harder to get that electron off. Which has the larger second ionization energy and why? Lithium or beryllium? Lithium. Why is that, Rui? Thanks, JD. I was waiting for Rui. Because? Because we're moving past the noble gas. Which is, JD? Removing a core electron. Lithium, because removing lithium's second electron is removing a core electron. All right. Oh boy, we're running out of time. I get stressed out. All right. Arrange the elements, oxygen, fluorine, and sulfur, according to increasing ionization energy and size. I like to do size first because that's the easiest, and then I can take everything from there. So size, what has the smallest versus largest? How are these ranked? Sulfur's largest for sure because it's way down the table and it's got a lot of shielding, right? Not way down the table. Level takes precedence here. Remember that? Does precedence have an C or an S, the first one? C. Okay, good. I did something right. All right. Now, compare oxygen and fluorine. Which one's smaller? Fluorine, so oxygen's in the middle. So ionization energy is kind of the reverse, right? The smaller the atom, the harder it is to remove that valence electron, that most loosely held electron. So it's going to be opposite. Do you all see why? All right. Okay. This last one. This one is rarely seen, and if it is seen, it's probably on the multiple choice. But you're going to college. You're going to take chemistry in college, so I think it's a good thing for you to know. Electron affinity, I want you to think about it as basically taking an electron and putting it onto an atom. Some atoms like electrons, like fluorine. As we go down a period, we're getting closer, not fluorine, I want to do francium. As we go down a period, we're getting closer to francium. If you had to get francium to take an electron, would francium want it? No. No, it's huge. Barely any nuclear pull on its valence electrons. It doesn't want it. So what would you have to do to make it happen? You'd have to put in a ton of energy. So to make francium take an electron, we'd have to put in energy, lots of energy. The most of all the metals. So what is the value on energy, not the value, the sign on energy when you're putting it in something? Positive. So these metals, all metals, have positive electron affinities because you have to force them. There is no such thing as a negative metal that naturally happens. You have to force electrons onto metals. But if this is true for that direction, then the opposite has to be true for going to fluorine. As you move toward fluorine across the table, these atoms get more and more excited about electrons, so they actually will release energy when they get an electron because they're so excited. Energy is released. And when energy is released, what's the sign? Negative. So your negative electron affinities are going to be more of your nonmetals, with francium having the most negative electron affinity. Fluorine having the most did I say francium? With fluorine having the most negative electron affinity. Francium, on the other hand, doesn't want it. It's going to have the most positive because you have to force it. Okay? That's all you need to know. Does that make sense? All right, we're going to work one problem, and then I'll talk about your review for the test because this is the last last lecture of the unit. Let's answer these as efficiently as we can. Magnesium is smaller than barium. Explain. Magnesium is smaller. No, we're going to answer it in terms of magnesium. Magnesium is smaller. Why? Magnesium has less shielding. You can't assume the opposite is true in all cases, so I don't want you to be just answering it with regard to the other one. Magnesium is smaller because magnesium has less shielding than barium. Okay, the ionization energy of S, oh Lord, is lower than that of P. So I'm just going to draw out my P orbitals here. You know, my S has 4, and my P has only 3. So why is it easier to remove the S? Easier to remove the last electron in S due to repelling forces in the p orbital. Okay? Not a ton of words, not that hard to answer. The energy required to remove the 4th electron in aluminum is significantly larger than the 3rd. Tell me about the 4th electron. Is a core electron, so harder to remove than the 3rd, and I'll put valence in parentheses because that's a valence electron. All right, this one, you're going to kind of just write, ooh, what did I do? Stop. Kind of write this in your own words. The energy change associated with gaining an electron, the electron affinity, is positive for some atoms and negative for others. What would you say? Some atoms require, how about require? Some atoms require energy to take an electron. And that, what kind of energy is that? You got to go back to the question. What does the requiring energy sign translate to? Positive. So some atoms require energy, which is positive energy values. And some atoms require energy to take an electron, which is positive. Other atoms will release energy upon accepting an electron, which is negative. to the wire. So the most important part, I could sit here all day and do examples, but it's not the same as you looking at these problems with your own head and your own vocabulary and writing answers. So we've provided you with these last 3 in-class problems. I want you to do them cold. I want you to get out paper and just do them, just like you were taking a test. And then you can check the answers. The answers, and they're scored like AP answers, okay? The answers are in your homework answer folder. It says answers to last 3 in-class problems. I think that's what the file is called, okay? So be sure to do these before the test. Tomorrow's PES, don't forget, you've got to know how to do that activity if you're not going to be here. It's not an unimportant activity.